All right. So I want to prove some facts about formerly real fields. In particular, formerly real fields are orderable, meaning that they can be turned into a ordered field. So let's see how do we prove that. So it took me a while to work out the proof, but I think we got it here. So first, let's define what it means to be a formerly real field. So a field, K, is formally real, if -1 is never a finite sum of squares. If -1 is not equal to any finite sum of squares. So for any m, any xi in k. Okay, so we cannot write -1 as a sum of squares. All right, so that's called a formally real field. And our claim is that if it is formally real, then it is orderable, meaning that it can be assigned an order to which it turns into an order field. So proposition, if K is formally real, then there exists an ordering on K such that K with this ordering is an ordered field. Okay, so we got this going. That's what we want to prove. And the converse is actually true as well. If a field is an ordered field, then it is also formally real. So it's actually if and only if condition. So this is kind of a neat characterization of ordered fields, actually. Um, all right. And well, what qualifies as an ordered field? And so a trick is to identify a positive cone. So we got to recall this. This is something that I proved earlier. But recall, uh, if a field K admits a subset called a positive cone, subset P, a what we call a positive cone, i.e., is satisfied the following property that P is closed under addition, P is closed under product, and that P make up everything. Oh, I just realized I forgot to prove something, but hopefully we'll come to that. P and P, negative P is everything, and P and negative P, they intersect at 0. So if it emits a subset called a positive cone, which satisfies these three properties, then K is K can be made into an ordered field. Okay. In particular, you just take uh, x less than equal to y if and only if that y minus x is in P. Okay. So that's kind of nice. In other words, in order to show that a formally real field is an ordered field, then we just need to exhibit uh, this positive cone business. Okay, so our goal is to construct a positive cone. All right. So how do we do this? The idea is we're gonna somehow first create these pre-positive cones and then exploit Zorn's lemma to find the maximal element being a um, positive cone. That's the idea. Well, it's a little bit of work. So let's see. So step one, take this P uh, to be the collection of subsets of our field, of our formally real field. Um, so in K, the posicon P in K, which is formally real. You gotta remember this. Okay. And we're gonna consider the collection of these subsets, these pre-positive cones, where P satisfy the following criteria. P is closed. P is closed on the product as well. This one is interesting. Every square is in P, and -1 is not in P. Okay, so these conditions. So this is what's gonna qualify as our collection. Now, this collection is not empty because if we take this P0 to be the set of sum of squares, yeah, sum M, sum xi in K, all possible finite sum of squares, then notice P0 plus P0, if you have finite sum of squares, that's a finite sum of squares, that's in P0. P0 times P0, well, if you take a product of sum of squares, like x1 squared plus dot 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 plus xm squared, y1 squared plus dot 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 plus yn squared. Then by distributing, you get something like x1, y1 quantity squared plus, x1, y2 quantity squared plus dot 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 plus xm, yn quantity squared. You get another finite sum of squares. So P0 times P0, P0 is closed on a product. It consists of all sum of squares, so certainly it consists of all squares because you just take singleton elements. And finally, -1 is not in P because in P0 because if -1 is in P0, then -1 is a sum of squares, which we say because K is a formally real field, it does not have any sum of square making the -1 number. So -1 is not in P0. So what does that mean? That means P0 is in our collection script P right here. So script T is not empty. Okay, so it's not an empty collection of sets, this script P. 3, script T has a very natural ordering, uh, is the inclusion, right? These are collection of sets, so take this. Now we claim, so this is certainly a partial ordering on script P. And we're gonna show that it obeys Zorn in the sense that every chain has a maximal element. So take any chain in script P, okay? Let's say script C. Um, then this is a chain and denote or let's say P bar, yeah, to be the union over the collections in script C. Okay. Then notice certainly that for each P in script C, P is contained inside P bar, right? So this is the upper bound. And well, it's only an upper bound if this is actually in P, right? So let's see if it's in P. To be in script P, though, we gotta satisfy these four conditions. Close under sum, product, contains squares, does not have -1. So let's see. So notice um, for each P in script C, -1 is not in P. So -1 cannot be in their union, which is P bar. So it does not have -1. For each P in C, it contains squares. So of course, the squares is gonna be contained in P bar. And is it closed under addition and product? Yes. For every X and Y in P bar, X is in some P1, Y is in some P2, and without loss of generality, because um, they're part of a chain. So let's say P1 is in P2. So therefore, X and Y are both in P2, hence X plus Y and X times Y are both in P2 because P2 satisfy closure, which of course is in P bar. Conclusion is that P bar is part of our collection. Hence, P bar is an upper bound of our chain. So any chain has an upper bound. Therefore, by Zorn's lemma, some maximal element exists. A maximal element P in our collection exists. Okay. And now we just need to show that P is a positive cone. So that's step 4. Our claim P is a positive cone uh, in K. Now, the collection of sets of script P sometimes is called the collection of pre-positive cones. So these may be called pre-positive cones, satisfying these conditions. But just details. Okay, so let's see. How do we show that P is a positive cone? Well, to show something is a positive cone, remember it's got to close under addition, product, the union with its negative, it's everything, and the intersection with its negative is the zero, just zero. Let's see. Because P is part of the collection, we already know that P is closed under sum and P is closed under product. So it remains to show that P union it's negative, it's everything, and P intersect it's negative is 0. So that's what we need to show, these two things. This box and this box. Well, let's first show the first box. So step 5, y is p union negative p equal to k. So let's assume it's not. Suppose not. That there exists some x in k, but not inside this union. So some x element is neither in P nor negative P. So we miss one. What does that mean? So we're going to consider P union X. Okay, this is certainly larger than P. Oh, a couple things. A couple things before we move on. If X is not in P or negative P, that X is neither 0 nor 1 nor negative 1, right? Because if it's 1, it is in P. If it's negative 1, it's in negative P. And if it's 0, then it is in P because P contains 0. So notice X is not plus or minus 1 or 0. All right. So the set P union X is strictly larger, and I claim it is contained inside P plus PX. Certainly, the set P plus PX contains P and contains X because one is in P. Um, we claim that P plus PX is actually part of our collection. And that's gonna violate our maximality condition. Okay, so we're gonna need to prove this. So this is our main claim that this is part of our collection. Well, to show this, A is it closed under product? So let's see. Take let's say a let's say this is a P plus QX and P prime plus Q prime X, P prime, Q prime, all in P. So take these two elements from this. And notice that there's some by factoring. This is P plus P prime plus Q prime X. This is in P. This is in P. So this is in P plus PX. So I took two elements from P plus PX. The sum is in P plus PX. Okay, that's clear. What about the product? Well, let's take the product. This is PP prime plus PQ prime X plus QP prime X plus QQ prime X squared. By working this out, this is PP prime plus QQ prime X squared plus PQ prime plus QP prime X. All right, so let's check this out. PP prime, that is in P. QQ prime, that is in P, because both of them are in P. X squared, a square that's in P. So now this is all in P, because sum of P, sum product of P, that's in P. This is also in P, so this is in P plus PX. Great. So it's closed under sum and product. Now to show that it's in the collection, it's got to contain all the squares. So, but all the squares are already contained in P, and remember 0 is in P. So this contains P, so of course contains the squares. So K squared is in P, therefore it's in P plus PX. Check, check, check. Okay. Now, what's tricky is to show that a negative one uh is not in P plus PX. So need remains to show negative 1 is not in P plus PX. Well, let's suppose not. Suppose not, then negative 1 is in P plus PX. Well, what does that mean? Well, that means that negative 1 is equal to some P plus QX, P and Q in P, which means what? If we move things around, it means negative QX is equal to 1 plus P. Yeah. And 1 is in P is in P, so this is in P. So negative QX is in P. And since Q is in P and P is closed on a product, this implies that negative Q squared X is in P. And since, well, can Q be 0? Well, here, earlier, this Q cannot be 0 because if it's 0, then P is negative 1, but big P does not contain any negative 1s, so that cannot be true. So Q is not 0. So 1 over Q squared exists and it's squared. That's in P. So because P is closed on a product, this means negative Q squared X times 1 over Q squared, which is negative X, is in P. So if negative 1 is in P plus PX, then negative X is in P. But we assumed that X is not in negative P. So that's a contradiction. That's a contradiction right there. So, so what does that mean? That means P plus PX is a element of our collection. This violates a P being maximal. Because P is now inside, strictly contained in P plus PX. It does not have X, right? So it's strictly contained. So contradiction. What does that mean? Well, that means um um P union minus P is K. So right, it contradicts this part, right? This part right here. Why is this? Right? Yeah, so it contradicts the suppose not right here. So this contradiction contradicts the suppose not. This previous contradiction contradicts the suppose not right here. So this contradiction is this contradiction. This contradiction is double underline is this contradiction right here. Double underline. Okay. So now we got this. We have the union of P and the minus is K. Great. So P union minus P is K. And lastly, because of our criterion, we also need to show that the intersection is 0. 1, 2, 3, 4, 5, 6. So this is the last bit I haven't worked out. So it remains to show that P intersect minus P is simply just the zero, the number zero. Okay, so we know, so if there is something else that is not, that is in both, so suppose not that, so first of all, it has zero, right? Firstly, zero is in P, so zero is in, which is equal to negative zero, is in negative P. Therefore, zero is indeed in their intersection. Okay, obviously. But we need to show that there is nothing else. If there exists some x not equal to zero such that x is in the intersection, well, what does that mean? I.e., x is in P and x minus x is also in P, which implies, minus x squared is in P because P is closed under product. And same deal as x not equal to 0, 1 over x exists, and 1 over x squared is in P because P contains all squares. So therefore, 1 over x squared times minus x squared, which is equal to minus 1, is in P because, again, P is closed under product. That's a contradiction because P does not contain negative 1. So it contradicts the supposed not. Hence, the intersection contains just the number 0 of the field. Therefore, we have a positive cone. Therefore, P is a positive cone. So, this P constructed to be some maximal element of these collections of pre-positive cones is a positive cone of in K, and K can be turned into an ordered field. Wow. Very nice. Happy days. All right. That works for me.